Hello, this video is finding volumes of solids of revolution using the shell method, which the shell method is basically using cylindrical shells to compute the volume. Now we'll talk about advantages and disadvantages of both this method and the disc/washer method that we've learned in a previous section. Now, the shell method, let me switch over to kind of an image from the book, is using, it's a tubular type of idea where it'll use infinite little tubular shells like this to come up with the volume. Now, I'll skip all the development on this. One of the key differences you'll see is that the representative rectangle dx or dy, it's parallel to the axis of revolution for this method where it was perpendicular before. Let's see if I can show that. Let me come back to my notes here. Now here are the two formulas. Yeah. So this essentially, with this horizontal axis of revolution, the shells are coming around like so. And this representative rectangle will essentially be the width of that, versus when you're revolving it or using the disc, if the representative rectangle goes up like this because it's actually representing the radius of that disc. All right. For some reason I can't draw here. I don't know what happened, but anyway. Seems to have crashed. All right, now it's back. So anyway, that representative rectangle represents the radius of the disc as it revolves around, whereas the shell method is going to be essentially the width of that cylindrical shell or tube or whatever you want to call it. This picture kind of looks like a tube from the textbook there, tubular type thing. So, all right, so it's going to be a little bit different. Now here are the formulas. Zoom in on this a little bit. So this is different. The variables are basically the opposite as what you do with the disc method. If we're revolving around any horizontal axis of revolution, we actually use functions of y. Now, if you want to look at the details, you can kind of go through that a little bit or find other resources that show, but we're using a variable y because of that representative rectangle being dy instead of dx. Oh. And yeah, the delta y, which of course will be dy. So this is variable y. So our function has to be integrated with respect to y, and it's going from c to d on the y-axis. And like I said, that gets you if it's a horizontal axis. Whereas, if we were using c and d for the disc/washer method, that would have meant we were revolving around the y-axis. So it's just the opposite. So same thing over here. So it's 2 pi, p of y is essentially going to be your height. Most of the time, the problems I'm going to do, it's just going to be y. But let me explain to you, even if I don't ever test you on this, or whatever the case may be, let me sort of explain to you what it means. So in this case, if it's the x-axis, it would be y. But if you were revolving it around the line, like say y equals 1, like so, revolving it, well, that's not a very good line, but I can straighten that out a little bit. Y equals 1. That distance up to that dy would be y minus 1. So it's y from the x-axis, but then the distance from here to here, if that's 1 right there, would be y minus 1. I'm not using a tablet to do this. I'm kind of using a mouse thing. So it'd be y minus 1 from here to here. But then it would be y all the way from there to there. So my examples are going to involve just basically either y or x. But I want to make that clear. Same thing on the x. It would be x minus whatever the vertical line of revolution would be. All right. So just the opposite then. If you're going around the y-axis, you're going to be using variable x, whereas in the disk washer method, it would be variable y. All right, so let's come down here. And then, like I say, the p of x will pretty much be, I forgot to mention h of y is whatever the function distance is out from the value, and then h of x then will be y as a function of x of that height. Okay, and this will be the horizontal one over here. Let's come down here and just take a look at a few things here and there. Now you'll see a lot of problems. Sure, they could be done by either method. They don't have to be done. Sometimes the shell method's better. Sometimes it's not. Sometimes I'll mention a case to where it's absolutely necessary. And I've got that coming up here in a little bit. And let's see. We've got this function, y equals square root of x, and some of my examples are going to show you how to do it the other way, just so you can see it by comparison. Okay. And we're going around the y-axis, so it's going to be a function of x. The p of x will be x, your horizontal distance coming from the y-axis. So like I said, that's pretty much either going to be x or y. You know, could be others, but, you know, I'm not likely to ask that on an exam, so... And then your h of x is square root of x all the way through here. Now, if this were to change, you know, the function took on two different shapes or something, then we would need two different pieces to solve this. But here it's just the square root of x, represents your height. So this formula has 2 pi versus the other formula with the disk method is just pi. And then we're going x-axis there, just the limits of integration, 0 to 4, x times the square root of x. And this is not a hard integral, just convert this to x to the 3/2. And we come down here and we just use the basic power rule. So it'd be 2 pi times 2/5 x to the 5/2, 0, 4. And 4 to the 5/2 minus 0 to the 5/2. 4 to the 5/2 would be square root of 4 to the 5th, which is 32. And you'll end up with 128 pi over 5. So let's take a look at this via what I'm calling disk/washer. And the reason why I'm kind of lumping, you know, those together, because they follow the same guideline, and they both disk and washer. The only difference when washer is when you have a gap and it's outer minus inner radius. That's the only difference, but it still follows the same procedure, you know, the same variables of integration. So disk/washer. Now, if you look at the picture as this revolves around the y-axis, it's definitely going to be a washer. So the shell method only required one integral to do this by cylindrical shells. This, using washers, it's taking, we have to take the gap into consideration here. Okay, so let's see what we've got here. Because essentially the shell is kind of taking, you know, their tubes or whatever, and they'll take on that gap already. So that's why the gap's already covered. Of course, then the gap gets narrower and narrower, you know, when you get to the origin. But let me go back to this picture again to show you if that's still, yeah, see, it already has gaps in it. So there's no outer minus inner in this concept for this, especially at least this problem. So the disk washer method. So now, though, we have to convert to variable y. So if y equals the square root of x, which is not hard to do, you just square both sides, that means x equals y squared. So we would do outer radius squared minus inner radius squared. And then now the limits of integration, instead of 0 to 4, they're vertical. They'll be 0 to 2. The outer radius is that fixed line 4, and the inner radius would be y squared. So this sets up exactly as it would have in the previous section for washer method. except now this formula only has pi. And let's see. So it's 4 squared minus y squared dy. I didn't work out the integral. It would not have been hard to work out. It just would have been 16 minus y to the 4th. Do the power rule. I just wanted to save time. But the point I'm trying to make is look what the answer ended up being, 128 over 5 times pi. So that they were identical answers, whether you did the shell method or the disc washer method. All right, let's take a look at this example. Oh, this is the instructions say up here. For 1 through 14, that was number 3. This is number 9. We're going around the y-axis. So obviously, you got to know. You can't tell just by this right here. So obviously, on any kind of question you would have on a quiz or test, it's not going to leave you hanging like that. It's just going to, each problem would be, the information would be self-contained within the problem. But anyway, so it's coming from those set of instructions. All right, so going around the y-axis, that means that representative rectangle is going to be vertical. Let's see. Because that's representing dx. So your p of x will be x, and then your h of x will just be the radius out from here to the line. The height, not the radius, which is 4x minus x squared. Now that's the height of this graph. However, that's not the height of the region that we're actually evaluating. The height of the region that we're evaluating is at the line y equals 4 minus that curve. So the height's going to be 4 minus 4x minus x squared. I kind of misspoke there. Yeah, the height of that line is 4x minus x squared, but the height of our region is 4 minus that. So, okay, let me clarify that. So, sort of got messed up there, but we're good now. So that's going to be x times that. So actually I worked this one out. Most time I don't mind these problems if you use a graphing calculator to work these out. That's fine, but I'll show you how to do it manually. Obviously, it's good. It's a good skill to have, and it's not a hard integral. So we got x times this. So I just kind of distributed through here, and I'll be careful because the minus is going to affect both of those signs, right? So it'll be 4x minus 4x squared, but it'll be plus right here, plus x squared. So that's going to be x cubed. 0 to 2. It's vertical. Actually, the vertical is same. So it's going from 0 to 2 horizontally, not vertically. Now, 0 to 2 on the x-axis. And then the antiderivative, looks like I erased something there. It's going to be 2x squared minus 4/3 x cubed plus 1/4 to the x to the 4th. Plug in 2, plug in 0. And then just kind of resolve this with common denominators. 8 plus 4 is 12. That would be 36 over 3. Makes that 4 over 3 times 2 pi would be 8 pi over 3. Would be for that volume. All right. Now this here's an example where you could actually solve this one. You'd have to do completing the square, and it would be a pain. This is much better. And here's what I was talking about, where the shell method can come into play. Is if you have to solve for like x in terms of the other variable, and it's either very hard or not possible to be solved, you would have to do it by shell method. Now this one could be solved if you switch the x and the y, but you got to do you got to complete the square and do a bunch of business there. It'd be kind of messy to solve for x in terms of y, completing the square. I say it's not extremely difficult, but it's much better to do it this way. Now here's an example of a function. Let's say if we had y equals x cubed plus x plus 1, then we could not solve for x in terms of y. we would have to use the shell method because we could not get this. Because remember, if we were to try to do this same problem that we just did, but I'm not going to just because it's, like I said, it's too messy to solve that, so why bother? But I like showing both ways, like on the last example, and we'll see both ways for upcoming problems here. But yeah, you would have to solve because you have to get, to use disk washer, you have to get X to go around the y-axis. It has to be variable y. So there's no question. So this, but not for the shell method. It stays variable x there. So. All right, so that's another kind of interesting point about the shell method is the algebra aspect of it for certain types of functions. All right, so I'll leave that there. So of course, that's in the notes. You can just kind of read that a little bit, but okay. Let's come down here. Now, this group of problems were revolving around the x-axis. So according to the shell method, revolving around the x-axis, we have to integrate as a function of y. Now this time we're looking at the distance going across here, not up and down. So you might think this looks like similar to that picture in the last problem where it's going to be like an upper minus lower, but no, we're going this way. So notice as you go across here, cross, you have the same function here, x equals y to the 1/3. The last one, because of the way we were revolving, yeah, for example, if we were revolving, we would have subtracted, in fact, this is very similar to that last, pretty similar to that last one, the one before, excuse me, I guess the one that was back up here, where we, that where we had to, it was the last one, excuse me. But anyway, all right, so we don't do that this time. It's not going to be subtracting because x equals y to the 1/3 is fixed, and then this will be y, that vertical distance. Like I said, it would be y minus something if you were revolving it around some other line. So it's just y times y to the 1/3, and from 0 to 8 on the y-axis. Yeah, I know it's strange getting used to this because you're used to doing these on the x-axis. So 0 to 8, even though it's revolving around the x, and you combine those together, you get y to the 4/3. 2 pi, 0 to 8, y to the 4/3. We use the power rule. Gives me 3/7, y to the 7/3. And you put in 8, and that's going to be the cube root of 8, which is 2. 2 to the 7th, 128. And then that's 6 pi over 7 times 128. We get 768 pi over 7. I went ahead and just verified that in Maple just to make sure. And Maple agreed. Now, let me show you this one, same problem, if you were doing disk and washer. So now we're going around the x-axis. So, going around the x-axis means we have an outer radius minus an inner radius. Then also to go around the x-axis, we must compute or change y in terms of x. Now that's not difficult. Well, that's already done right here. What am I saying? I had to convert it from there. There it is. Y equals x cubed. So we're going to have the upper function is 8. The lower function is x cubed. Now the disk/washer method requires us to square both of those. I did not work out the math on this one just to save time. Like I say, if you ever have any questions, let me know. I just wanted to kind of show the setup with these other methods just so you could see, work it one way, then show the other setup and show that it's equivalent. So it's this time, though, you go on the x-axis for the disk washer. So this time it's 0 to 2, 8 squared minus x cubed squared. So we'll just be integrating 64 minus x to the 6. Real simple. It'd be 64x minus 1/7 x to the 7th. And then put in the 2, put in the 0. We only have 1 pi here with the disk washer method instead of 2 pi. And comes out to be the same answer. So that's good news. We like that. Now this one, we're still part of the same block of problems, but now we're about to hit something where the shell, is less than desirable. we look at this function. We're going around the x-axis. So our representative rectangle is going in the x direction. One thing we're going to mention to get down here at the end, but I'll go ahead and say it now. One difference between the shell and the method and the disc and washer is your representative rectangle is always parallel to your axis. Whereas in the disc and washer, that rectangle is perpendicular to wherever the axis is that you're revolving it. So this diagram, for if it represented a disc washer, that diagram represents, the going around the y-axis. Those rectangles mean they're going around the y. Here it means the x. But the problem is we don't have the same left and right bound here. In other words, like let's go back up here, this last example. Notice that you've got this y-axis as your fixed left bound, and your right bound is that curve. So you got to have the same left to right. I've seen some videos that explain it. Just kind of imagine if it was turned over and kind of going lower to upper, but that's the lower and the lower value for x, the upper value for x. Sure, you can think of it that way, but I find it easier just to say left, right, basically. So, like we did when we found the area of curves, but on the with x in terms of y. Remember, it was always right minus left. But if you did tilt it 90 degrees to the left, it would be upper minus lower. But I'm going to stick with my right minus left. Anyway, so notice that this graph, it has, where I separated, I put that line in there to separate. So it's got two different left bounds. Part of the way, it's y-axis. And that's going to be from 0 to the square root of 2, because when I put 0 in for this function right here, it's going to be the square root of 2. And that's where that graph starts. The blue line represents y equals the square root of x plus 2. Now it's kind of curving along there. And then the other line is y equals x. So you have the same bound on the right, but you have two different left bounds. So that technically means we have two separate shell method integrals that would have to be added together. Now let's see what we got. Now, y represents the distance, x equals y, that represents the horizontal distance across, but the other function, let's look at this. So this is going to go, for the bottom one is going to go from 0 to the square root of 2, and it's going to be y, and then that's going to be y right there. Okay. Now, this one has to be a function of y. So that was obviously easy. If x equals y, y equals x. Obviously this one, though, it's not hard. But let me just mention, you got to solve that for x in terms of y. So you square both sides, and then you would get x equals y squared minus 2. Like so. So this distance across here for this upper part is y minus y squared plus 2. It's the difference of the right one minus the left one. And then the limits of integration vertically here are going from the square root of 2 up to 2. Now, to get the 2, you can actually solve that if you wanted to, algebraically, or if you can just kind of visualize and see what it's going to be. Like when you put 2 in there for x, you'll get the square root of 4, which is 2, and you'll get 2 here. If you solved it, you would just set these equal to each other. And then, or you can, solve these in this form equal to each other. But anyway, you're going to end up with y equals 2, x equals 2, and then of course that means y equals 2 because y equals x. So you can solve them equal to each other and work it out, or you can just kind of figure out what you think it's going to be, and it's going to be 2. So it requires 2 of these, and then I just went ahead and let Maple take care of the integral here, and it's simplified to 10 pi over 3. Now, let's look at this as disk/washer. So we're going around the x-axis. Now, it is going to be a washer, but it's not going to require two different integrals. The washer always has something minus something, but it's one integral. So I think I kind of like the washer here, so it's going to be upper minus lower. So the upper is the square root of x plus 2 minus the lower, which is x, and it's also it's going to be 0 to 2. Just by coincidence, they're both the same limits. So it's the upper squared, the square root of x plus 2 squared, minus x squared from 0 to 2 with pi out in front. And there we have it. And this one I did work out. The other one I didn't want to mess with it. So did I work it out using... Well, I didn't. Okay, I didn't verify it with Maple or anything, but or technology or anything, but I'm pretty sure it's right. So there it is, square root of x plus 2 squared minus x squared, easy integral. Worked it out, there it is. Just take the antiderivative, 1/2 x squared plus 2x minus 1/3 x cubed, 0 to 2, plug it in, and you end up with 10 pi over 3, so it matches. So in this case, I think washer is actually better than shell. A lot of times, shell will be better than washer, so it's weird how that works. You know, there's not really one. I mean, unless you have the scenario where you cannot solve the variable in terms of the other, then it's shell. But this is I think I thought this was a little bit better here because that was a little tricky to come up with that mess for the shell method. All right, let's see what else we have here. Now, this one, let's see. I'm saying that the disadvantage of the shell method, so we have two different boundaries. Left to right, see, two different right boundaries. That's a typo. I got myself, I guess, confused with the last problem. Two different right bounds. So it has to be separated. Well, I didn't draw the dash line. I guess the dash line was already there. So let me set this one up. And I'm going to kind of go back to the book and sort of show you a different kind of thing where this actually depends on where you're revolving. It's actually easier with the shell method. But this one is not. This one, it's because of the different right bounds here. So you're going from your y, they're both still at the distance y. That's still the same here, the y and the y, because we're all revolving it around the x-axis. So that's why this 1 represents the distance from 2 to 1, because it's a fixed distance. It's not variable. But up here, and now you're going from 0 to 1/2 vertically. So that goes from 0 to 1/2 where the dash line is, and the next one will go from 1/2 to 1 right there. So you got 2 pi. Now you've got, so the y again. Now you have this, which if y equals 1 over x, it's easy to solve. That means x equals 1 over y. That's not difficult. But that height is 1 over y minus 1, because that's 1 right there. That's not flush up against the axis. You know, so it's not 0. It's minus that 1 right there. So it's 1 over y minus that 1 right there. Could use marker like that. Yeah, that 1 right there. And that's where the 1 over y minus 1 comes over. All right, I decided not to work this one out. Because, like I said, most of the time the working it out, it's not that big of a deal. It's the setup, mostly. And, of course, I would to do that problem, I would distribute through the parentheses before I, integrated. Well, you kind of have to. So that's 1 over y minus 1. So that part is pi over 2. Now let me come down here and show you this using the disk / washer. It's actually just a disk method if you're going around the x-axis. There's no gap. Now we're thinking vertically. Think of a vertical rectangle now. So I'll try to draw something here freehand without a... This isn't a tablet, so it's probably not going to look very good, but that's not too bad. There it is. So now we're taking that around the x-axis. There's no gap. It's not even a washer. It's just a solid. It's a complete solid, no gap. Your upper function's 1 over x. Your lower function's just the x-axis, 0, so it's just 1 over x. And then now your limits of integration are on the x-axis, not the y-axis like they were with the shell method. Going from 1 to 2, so it's just literally this. It's pi times 1 to 2, x-axis, 1 over x squared dx. I didn't work that out, but 1 over x squared would be easy to integrate. X to the negative 2, just do the power rule, work it out. Looks at that. Pi over 2, same answer. Now this, let me switch or show you something kind of interesting. There's an example in this particular book, and find this elsewhere, where it has that same kind of shape. Now this one, though, it's revolving around the y-axis instead of the x-axis. So it's just the opposite problem. The disc and washer method would force you to have two regions added together, two pieces, but not the shell, because if you're going around the y-axis, your representative rectangle is vertical, and this time that takes advantage of the same advantage we had the other way for the disc method. This one, the shell method, has the advantage right here because it's the same upper function. So it's kind of, that one actually, if it was going this way, the shell method's easier. It's one integral. And you see they did two of them up here and got the same answer. So I thought that was kind of interesting. Makes that kind of confusing. So if this same problem we just did, if that was going around the y-axis, it would be easier with the shell, whereas this one was worse with the shell. All right, so let's see what we got here. I think we're just about done here. So once again, it's kind of showing. I found a couple of pictures there, just sort of showing the one on the left here is it's going around the y-axis with using discs / washers, and this is doing it using shells. But the difference between the shells is you're interested in that height right there. That's your D right here. That's your delta. So right there, that's your representative rectangle. Whereas going this way, it's that radius of it that's your representative rectangle. I mean, similar shapes are both circular, but this shell is using a different type of measurement. So, and here's what I mentioned this earlier, and here's where it's actually saying it in writing here, that if you're using the disc / washer method, the representative rectangle is perpendicular to your axis of revolution. So you see that's perpendicular to y. This vertical rectangle is perpendicular to x. But for the shell method, they are parallel. So that vertical rectangle, delta x, is parallel to the y. And then the delta y here is parallel to the x. Okay, let's take a look at this example where we're going to take these two functions and we're going to find the volumes of solid by both methods and both axes. In other words, we're going to find the x-axis revolution using both disc / washer and shell. And then we're going to revolve them around the y-axis using disc, washer, and shell. So here are our two functions. The blue one is the square root of x plus 1. And the red one, the parabola, is x squared plus 1. And there's the region shaded in yellow. So we're going to revolve this around the x-axis. And revolving this around the x-axis is going to be the washer method, because there's definitely going to be a gap in there when it comes around here. So what we're going to look at is we're going to look at essentially outer radius minus inner radius, in this case coming from the x-axis. So the outer radius would be the square root of x plus 1, the blue line. The inner radius would be x squared plus 1. And then limits of integration will be on the x-axis. So this formula uses pi, so it'll be 0 to 1. And so, like I said, the square root of x plus 1, that'll be squared, because r squared, big R squared minus little r squared, minus x squared plus 1 squared. That would be the disc washer method. Now, for the shell method, we have to change these over to x as a function of y, which will also be needed when using the disk washer, when you're revolving around the y-axis, it will have to be in terms of variable y. So we'll get variable y here. And we are looking at, this formula involves 2 pi instead of pi. We're going to have vertical limits of integration. So if you look at this graph, y is going from 1 to 2. And let's see. And if you weren't 100% sure that that was 2, it'd be real easy to check by putting 1 in here. The square root of 1 plus 1 is 2. 1 squared plus 1 is 2. So they're intersecting at the point 1, 2. Now, the shell method, we're going to be using, it's the, P of y, H of y thing. And the P of y, in this case, would be y, because we're going around the x-axis. If you were revolving around some other line, y equals something, you would just subtract. So if you were revolving around y equals, say, -1, it would be actually y plus 1, because that would be the distance from that line. And let's see, so we're going to have y, and then we're going to have essentially, so here they are, excuse me, there's x solved in terms of y for the first one. Because you move the 1 over and you square both sides to get rid of the square root. And then for x, y equals x squared plus 1, move the 1 over, we get y minus 1, then you take the square root. So now we're looking at this one essentially as the right minus left going in the x-axis direction. I like to use right minus left. Some people just treat the x-axis as being vertical, so it would still be looking upper and lower, but I like to only use upper and lower when I'm talking about the x-axis. That's what I prefer. But if you turn this graph 90 degrees and going up the x-axis, the red one would be the upper one of the two. Now, we don't square these functions, we just take the difference between them. So it's square root of y minus 1 minus y minus 1 squared, and then with the y in front. So it's an outer radius, inner radius kind of idea, but we don't square them. Now I'll put both these answers in maple, and let's see what I got here. Well, that's terrific. 29 over 30 times pi. So I feel pretty good about what I did there. Let's take a look at the x-axis, the y-axis, excuse me. That was the x-axis. Let's do the y-axis. Let's look at washer, because going around the y-axis will also have a gap. You see, the gap would be between the y-axis and the blue line, which is this function, which is the y minus 1 squared. And so we're going to go from 1 to 2. And it's going to be outer squared minus inner squared. The outer is the red, which will be the square root of y minus 1. So that's the outer. So it's the square root of y minus 1 squared minus the inner, y minus 1 squared. Outer minus inner, we have pi. And I maybe forgot to mention, or I'll mention again if I did. Remember the shell method formula has 2 pi there instead of pi. Pi for disk washer, 2 pi for shell. It's outer, essentially minus inner, both of them squared. The shell method, we use, even though y-axis, we use variable x, it's always the opposite variable. So your p of x is going to be x. And so yeah, anytime it's around the x-axis, p of x will be x with shell method. Same argument that I was using, for the y, but if you revolved it around some other line like x equals -2, and that means your p of x would be x plus 2, because it would be x minus a minus 2. But if you're just only using x-axis and y-axis, then it's definitely just x and y for the p of x. Now this will be upper minus lower. Still kind of an outer minus inner thing, but it's upper minus lower. So it's going to be the square root of x plus 1, and then x squared plus 1 will be the lower. So you see it's the square root of x plus 1, no square, minus the lower, which is x squared plus 1, and then the x in front, 0 to 1. Let's see. So put both these in maple, and look what we have here. Both answers are 3 over 10 times 5. So I feel pretty good about those setups. All right. That concludes this video on volumes of revolution by the shell method.